So the title of my talk is Overdamping in gyroscopic systems composed of high loss and low lossless components, and it is a joint work with Hennenfent from Florida Institute of Technology. This work grew out of our interest to magnetic materials, particularly to the fact that magnetic materials having useful properties used in many devices also are known to be very lossy, and the fact that they are lossy creates problems in efficient use of those materials. Things we knew that many composite materials have nice properties when combining different materials, that composite inherits some properties from one component, where some other properties from another component. So it was conceivable that a composite magnetic material still can have magnetic properties and have low, or at least lower losses, so to be less dissipative. And we worked with Aaron on this project for quite a few years now. So here is the list of our works on this topic, including our last work, which we report today, this on overdamping phenomena. And the initial work where we discovered that in fact it is possible by demonstrating, by showing an example, an interesting example of a composite medium, a simple composite medium which did exactly what we wanted. So we take raw magnetic, bulk magnetic material, make a simple composite structure, layered structure, and we find that the composite structure had pretty much same magnetic properties within a good frequency range, whereas the losses were significantly less. So then we tried to understand, that was an example where it was shown clearly that it is possible to design a material like that. We did not understand then how it happens, what are the conditions to enforce in order to provide some guidelines for designing different magnetic materials or other dielectric materials which inherit one properties, good properties, whereas some other undesirable properties are suppressed, like dissipation, absorption. So on this slide, I just, you can see here that what I already said, that these materials are useful in many cases for many interesting applications, and the losses are detrimental. And here is this idea was in this paper with Ilya Vitebsky, and also similar subject was addressed in another paper quoted here. So here is it, this example. I want to show you how simple it is. So here is a scheme of that magnetic layered structure. A here stands for anisotropic dielectric material, F for lossy magnetic material. Anisotropic material is assumed to be low loss. It maybe even doesn't have to be anisotropic, but this was an example. So we designed, it was a proper design of this structure, namely a choice of the weights here, and then we verified the strength of magnetic properties as it measured by Faraday rotation. So you can see on this slide, red line shows the Faraday rotation for the composite medium, and this dashed blue line for the bulk material. It's frequency dependent, of course, so you can see that Faraday rotation for the composite material is even better in this frequency range. And on this next picture shows you the absorption or dissipation. Dissipation of the composite structure was at least an order magnitude lesser than original bulk material. So that was an inspiring example, and we wanted to understand the mechanism, if there is any general mechanism, or this is something so special that to find some answers to this somewhat counterintuitive behavior. It's, I think, counterintuitive indeed if we think of a structure with embedded, say, we have lossy material there. It looks like the more loss we put in the material, then the overall losses for the composite material should be higher. But this is, it turned to be not the case at all. Now, that intuition about that adding losses should increase the losses overall, in fact, has some basis. Namely, it is true if the losses are very small. If the losses are very small and you make them a little bit higher, that intuition does hold, that the composite material will have loss similar, will a larger loss if you increase. But if you keep increasing the losses, then something happens. So hand-waving argument which I had at that time was, if you have highly lossy material, it affects dramatically the scattering. And so it causes as much scattering as it causes losses. So in fact, it is possible that some modes exist which are expelled from lossy material, and then they function and provide for useful property. But that was just a speculation, that how one can quantify that, and there is any general analysis which can confirm or be of a guidance in order to achieve a composite structure like this if, say, we play with different materials. So our main objective was to achieve this low loss dielectric material. As far as the theory is concerned, to have, first of all, we have to address the issue in the general theory, what represents magnetic, without going in detail. So, and also to relate an abstract subject to physics, to some physics. The best way to do it, in my opinion, is to construct Lagrangian structure for it, which is essentially energetic description of your system. Then magnetic properties can be associated with what is called in these settings gyrotropic or gyroscopic property. So I will talk about this a bit later, how it is, for those who don't know what gyroscopic means. It's reasonably simple when the Lagrangian structure is introduced. And so then, since gyroscopy is a very general property and can be modeled theoretically, then one can introduce losses properly and see what is the trade-off when you introduce more losses, how they affect gyroscopy and so on. So as I said, that advantages of the Lagrangian approach is that you have to start with one function and then everything is derived. Evolution equations, all physics is put in the, all your know-how is put in the designing a Lagrangian. Then the rest, mathematics, is handled nicely by Lagrangian variational principles. Then evolution equations can be derived. We know what the energy is, how the transfer of energy occurs from one fraction of the system to another, with clear and precise energy conservation, and also possibility to model magnetic properties as general gyroscopic. So without going in detail, elaborate description of the electric media. And if the property is indeed so general that can be addressed by gyroscopy, then it's clear a very general phenomenon, not necessarily for magnetic materials. So here is the our Lagrangian framework. So we denote by capital Q the set of degrees of our variables, QRs, degrees of freedom. We have capital N degrees of freedom. Then, according to the general idea of describing a physical system with its Lagrangian, Lagrangian is the quadratic function for linear system, and we consider only linear systems here, is a quadratic function of Q dot, which is time derivative of Q, and Q. So here we come with this matrix, alpha, theta, theta t minus eta, which in general is supposed to be kinetic energy minus potential energy. This is what constitutes the Lagrangian. Then one can also, according to the Helmholtz idea of energetics, we're supposed to write an energy. One possibility for the energy could be Hamiltonian, which is constructed out of Lagrangian canonically. Then, if we assume that Hamiltonian has a familiar representation by kinetic energy and potential, then kinetic and potential energies can be then uniquely defined. If we have just Lagrangian, you cannot do it. So, if our original Lagrangian as a dynamical system has this form, then we arrive at the following expressions for kinetic and potential energy. So now I can comment what is the gyroscopic properties. A simple Lagrangian system can involve only quadratic form of Q dots and quadratic form of Qs. But if there is a mixture between Q and Q dot, you have a gyroscopic system. Physically, a gyroscopic system indicates that you have forces which depends on velocities. If this physical manifestation of gyroscopic forces which depend on velocities. And of course, there are certain constraints should be put. If there are forces which depend on velocities, then for the system to be consistent, so we assume further that alpha and eta are real valued matrices, which are also positive. They are real valued, of course symmetric, that's self-adjoint. Both positive, this is positive kinetic energy is a must. The assumption of positivity of eta means that we deal with a oscillatory system. It should be stable. This is also general condition, and now theta is supposed to be skew symmetric for the whole thing to properly define gyroscopic forces. So in fact, another definition of gyroscopic forces is these are forces which do no work. They do no work. It's important. This is how they different, say, from friction. Friction also depends on velocity. So it's easy to see that for a proper Lagrangian system, gyroscopic forces depending on velocity must do no work. They still can modify the dynamics, but they do no work. In other words, they're always orthogonal. Motion is always orthogonal to forces. And from that consideration, you have this condition. Okay. So now, how we introduce dissipation in the system, also standard way to do it, from canonical texts on Lagrangian theory. Then here we have, so this equation in general, this equation, this, wait a second, how we wrote it? Yeah, okay, so the canonical equation, early Lagrange equation, would be that this quantity, which in our case represented by this expression, has to be 0. Then this would be early Lagrange equation. Now, if we want to introduce more forces above variational formalism, just like dissipation, it is done by replacing 0 with an expression representative, say, friction or absorption. So it is done canonically using Rayleigh function, where this is a quadratic non-negative form like this, and maybe some other forces if needed. Okay, so here is a Rayleigh dissipation function. It's a quadratic function. We assume to scale the losses roughly, we introduce scalar parameter beta, and there is a matrix R, which is supposed to be real-valued Hermitian non-negative matrix, which describes the losses. So we assume that this matrix can have a rank lesser than maximal rank, which means only certain degrees of freedom are susceptible to losses, which is relevant to the composite materials, where different composites components correspond to different degrees of freedom. So then the canonical conservation law, which is a derivative of Hamiltonian, is 0 when we have friction, is replaced with this equation. So if there is no F, we obtain this conservation law, which actually says whatever the energy disappeared or appeared in the system, it was exchanged with whatever provides for Rayleigh function, a system which absorbs energy or kicks it back to the system. So to crudely, in this very general environment, assume that we have a composite medium, we assume that the fraction, that the rank of the matrix of losses is this ratio, and R to N is lesser than 1. Or normally we assume that like we have 1/2, say 50% of the degrees of freedom susceptible to losses. Of course, if we assume that there are very few degrees of freedom, you remove the losses. But then, if, say, in the case of magnetic material, losses represent a useful property coupled, say, to magnetism, then this will not be a good structure. So here is this assumption, delta R is lesser than 1. So now to think about something related to electromagnetic theory, we can consider a circuitry which has all the elements which are modeled by general theory. So you can have a concrete structure before you. Of course, we can design also a mechanical structure, but things, we're talking magnetic materials and work with engineers in electrical, they prefer to see circuits rather than mechanical oscillatory systems. So here is the simple circuitry. This circuitry has, as you can see, has an inductance, capacitance here, another inductance. This E1, E2 are driving forces, external forces, whatever. And here is this element, a gyroscopic element called gyrator in electrical engineering, which introduces the gyroscopic forces. So real devices, gyrator is normally based on some kind of Hall effect. Okay, so here is our circuitry, and we produce and show you examples. We will look in detail at these examples. Yeah, by the way, I forgot to say that here is our resistance. We see we put it here in one place, so it will have the corresponding matrix R will have less degrees, will have only few lesser degrees of freedom, which are susceptible to losses, not all of them. Okay, and so let me go further. Now you see this busy slide. I don't expect you to look at all the detail, just to simply see that everything can be done explicitly for this particular example. You can write everything, all these matrices, and you write evolution equations. You can see any detail you want. And we also use it when we produce numerical, when we calculate it and want to show you the a picture, a more picture which is probably easier to understand than all these formal things. Of course, you can see here explicit expressions for potential energy, for kinetic energy, and so on. Of course, the simplicity of example, you can have very messy system which will be handled as similar to this. We chose a simple system so you can see easily all details. So now our first step is to rewrite the system in another form, which probably familiar in this audience, in the form when we have an evolution equation which involves a Hermitian operator, because the system is conservative. Now it's interesting that it cannot be seen at once that when you introduce gyrotropy, that you can rewrite a Hamiltonian system in the form of standard spectral problem. It is true only for oscillatory systems. It is not true in general. And in fact, there is far more involved spectral theory known as Krein spectral theory is associated with so-called pencils, equations of the second order, which is much messier than conventional spectral problem. And it is not that any Hamiltonian system can be reduced, as we believe often, to a simple spectral problem. It does reduce though, it is reduced though, but in the case when the system is oscillatory, not so stable, then, as we show, it can be done. So what are the conditions here? So if original variable is v, which is q dot, then we introduce standard variables p and q, where p is the canonical momentum. Then here is one can write explicit expression in these variables for the Hamiltonian. Then the dissipation then is modeled by this expression, matrix B. You remember it is dissipation is introduced on the top of variational principles directly into the early Lagrange equation, where it's clear where the forces are. One introduces after Rayleigh, with Rayleigh function, the dissipation. So here is explicit transformation of the original system involving the following matrix omega in the form I, which is imaginary unit, and then the following form k, j, k, t, where t is for transposition. Matrix B, after the transformation, has this form. Then F is this for the forces. Then J is this matrix, it's Q-symmetric. K is this matrix, this diagonal matrix times this. So you can see here this term which describes gyroscopy. So it's easy to see that this metric is self-adjoint. So in fact, now the operator which governs evolution equals to the self-adjoint operator omega, and then losses are introduced where, via this expression with the matrix B scaled with the parameter beta. So here is the system we are going to study now, and study its spectral properties. So I emphasize again, the ability to reduce the analysis to spectral problem involves this explicit transformation and assumption that alpha and theta are both positive. You can see if theta is not positive, this matrix will not be Hermitian, and then you don't get standard spectral problem, and you have to deal with very complex situation which is described in only a couple of books I know. In spectral analysis for crime system is not very well developed. There is no perturbation theory, I know, so then we would not have any tools to study that. No, anyway, this is for what we need is more than enough as far as the general settings are concerned. So now we would like to study the system and look at its eigenmodes and how they indicate the desired properties and what now information we can extract with these seemingly very general settings. So we introduce eigenmodes as conventional down spectral theory. These are time harmonic expressions like this, where zeta, so it's a constant, then this time harmonic with the assumption, of course, that zeta for lossy systems can be now complex number, not real, necessarily, okay? So zeta has a real part of zeta is the frequency, physically, whereas imaginary part with the sign minus is the so-called damping factor, according to common terminology. Then we have a standard spectral problem. Then evolution problem is reduced to standard spectral problem. Then we introduce very well known in electrical engineering for particular application concept of quality factor. Quality factor, I remind you, defines conceptually, if you have a oscillatory system without losses, it oscillates forever, right? Now, if you introduce losses and put it in this regime, it oscillates and say slowly loses the energy. Quality factor defines how many cycles it takes for the energy to decrease by factor 2. Okay? So, formal definition of the quality factor, which of course depends on the regime. Different regimes then can have different quality factor. Why not? It turns out that this well physically defined, there are, if you look the literature, slightly different definitions of quality factor which are not strictly speaking equivalent. In most of the situations they're almost the same, produce almost the same result, so we take this as a clear-cut definition which works perfectly well in general setting. So it's energy stored over energy loss per cycle, and then it turns out there is a very simple formula for this quantity associated with every mode. It is just 1/2 of the absolute value of the frequency divided by a damping factor. So it's an interesting quantity. Look at this quantity at this ratio. So it's natural. We naturally define losses with a damping factor. It's obvious. But this is much more subtle quantity. It relates damping factor to frequency. For example, quality factor can be low for fixed gamma if omega is low. And if omega becomes 0, then quality factor is 0. And this is interesting. This is what can happen in systems. And this phenomenon, when frequency becomes 0, is called overdamping. It naturally occurs when you increase losses. If, I don't know, if you look even at damped oscillator, all this is well understood from that very simple example. The system can be underdamped and overdamped, and there is margin, of course, in between two. So once again, you will see a slide. Yeah, here is a definition formal definition what is overdamped. So overdamped regime is defined, or say we define it for harmonic functions like eigenmodes. It is defined as follows. We consider complex number zeta associated with a mode. It's complex frequency, okay? Its real part for overdamped regime has to be exactly 0, so no oscillations whatsoever. And underdamped, if it's not 0, so it's still oscillatory. Now, for applications, obviously, most of electrical applications work for non-zero frequencies, not to mention high frequencies. So the overdamped phenomena, it's an interesting phenomena which explains a lot of what we wanted when we wanted to see how it can happen that a composite system has low losses, and what happens to the modes which extract the energy. So in fact, they become non-operational. So if the frequency, for example, of the lossy mode is 0, and we excite system at fixed frequency, that mode does nothing. It does not extract energy from the system. This gives you an idea how the general setting can explain this phenomenon that the system can be low loss when there are a lot of losses. So there are modes which of course send these losses, but they don't operate at the frequencies you want. Okay, so here is now choosing certain parameters. Here we show a situation when there is no gyroscopy is 0, so gyrator parameter is 0, and we have 4 modes, okay? So what happens also from our previous work we realized, when parameter beta, which scales losses, increases, the modes split cleanly in 2 classes, high loss modes and low loss modes. There is a clear-cut split in 2 classes. Now you can see this here. We have 3 modes here. 1 mode will be high loss, and 3 modes will not be high loss, will be low loss. So here is the high loss modes. You can see that imaginary part of zeta, or damping factor, it's minus damping factor, gets large as beta increases linearly. No, after some point, of course, there is some non-trivial behavior here, they're almost linearly. So this is high loss mode. The larger beta, the lossier the mode. But look at these modes. The other 3 modes, green corresponds to 2 modes because this is absolute value of, corresponds to 2 modes. Things they have identical because of the symmetry, they appear with the same curve as you planned imaginary part. So you can see there is a critical parameter. Here you can see by these cusps, and you can see for the other 3 modes as beta increases. So beta increases, but first the imaginary part absolute value grows, but then growth stops, and all of them go to 0. This is this phenomena we observe now in general. There is a part of the system which has more and more losses, but 3 modes out of 4 become low loss, and almost no, for large enough beta, there is almost, the imaginary part is almost 0. And we also have asymptotic formulas and more. This movie I cannot play because I did not download this to this computer. So now we can look at spectral symmetries. So we use a lot of standard, this is very standard and simple theorem or lemma about the spectrum. If you perturb the spectrum, then perturbed spectrum cannot move too far from the original spectrum. And now one can use it for clustering. Suppose your spectrum was degenerate, then it can split a little into a cluster according to this simple estimate. So here is the fundamental symmetries we have for our system. Modal symmetry, if there is an eigenmode of this form, then there will be an eigenmode which is conjugate of this form. I mean, this is immediately follows from general setup. Then we have the spectral symmetry, that the spectrum is symmetric with respect to imaginary axis, which can be formulated as if zeta in the spectrum minus zeta bar is also there for any beta. And also this useful estimate, which is we call clustering, which are helpful to distinguish some basic properties, and we use this to see clearly the separation of modes in different classes. So in this also busy slide, we have a theorem. I just explain you in words what's going on. First statement, which we knew from the previous work, there is a clear-cut split of the modes in two well-defined classes, high loss HL and low loss HLL. Two very well distinct classes. In particular, they can be distinguished by judging where the zeta is by simple inequalities, which distinguish them clearly by clustering. Okay? Now the dimensions are also well defined for this quantity. High loss modes have the dimension exactly the dimension of matrix of loss. NR was the degrees of freedom susceptible to losses, and this is the dimension of this space. So we know exactly how many lossy modes we will have, high loss, and then respectively the remaining part, low loss, will be the rest of the degrees of freedom, which is this difference. Now you can see here that for high loss modes, one can write at will the following easily, the following estimate about the quality factor, the figure of merit for the how good is the mode in terms of the losses. There is an a priori inequality of this form where you can see beta in denominator. So you can see here as beta will increase, then this approaches 0, which means that quality factor of high loss modes dives down to 0. And the opposite statement holds for the low loss modes. The damping factor minus imaginary part for the low loss modes approaches 0. So this is clear separation by quality factor for the two modes, two types of modes. And this is super general yet, just with very little detail about the system. So it turns out very interesting in terms of the tools we use. This is probably the only one example I have of using this, what sometimes we call it duality, but it probably called duality in some other work, so, which is known in mechanics. So what happens, we have kinetic, suppose we have a simple system without gyrotropy. Then a transformation which switches kinetic and potential energies. So what happens to the system if you switch them over? I don't want to go with an interesting philosophical, almost philosophical discussion about this duality of energies. You have one energy representing motion, translational motion, kinetic energy, and so-called potential energy representing some other motions which are not translational. And so if you switch over, because formally when you write equations, they look pretty much the same, but of course quantities will change. But we, in fact, have found that using this transformation allows to produce rather non-trivial estimates, which we don't know how to do it differently. So anyway, the dual transformation switches A and alpha. And so this is, of course, formal definition. You can see alpha and eta switched. We assume here that both are non-negative, positive. Because kinetic energy must be always positive, where potential does not have to be in general. But we consider both positive, and so we introduce this duality transformation, which we found very useful. then there is a proposition which relates neatly all the quantities of dual system to non-dual for eigenmodes. So the spectrum of one is related by this simple formula minus inverse of the spectrum for dual. Now, of course, if you remember formula for omega from Damp oscillator, that they come as a ratio, elastic to mass. Then if you switch them, of course, the frequency become minus frequency, also the sign minus here. Okay. Then the qualities factor also immediately can be related by the following formula. And then what is important, as you will see, the estimate, this is a very nice identity which we use when we write inequalities, which allow us to separate cleanly different situations of interest. So as you can see here, we make a comment, connects high loss for dual system with a low loss, a subspace of this, of the invariant system, which we first observed in simple system, and then duality allows to lift it to very general system as a canonical way to now split low loss in two classes. So low loss modes by themselves naturally split into classes, as we can say now, by their quality factor. So there could be low loss modes with low quality factor, and they are related to high loss mode of the dual system. Very interesting connection, and which we use. So you can see that this decomposition of low loss in two spaces, subspaces canonically, with the index 0 and 1. 0 corresponds to the high losses, and ultimately low or zero quality factor. As you can see, the estimate for 0 is this estimate. As beta increases, the quality factor for this low loss also will go to 0. Okay, so that they are not oscillatory either. There could be low loss modes which are not oscillatory. And this is a clean way to separate them. Whereas the other class corresponds to low loss modes which have high quality factor. They are oscillatory. And you remember quality factor was the ratio of frequency to damping factor. So damping factor goes to 0 for low loss, and omega cannot go to 0, at least too fast, not to mention if it's fixed. Then of course the quality factor will approach infinity. Okay. So this, and I have how many minutes?
7.
7, okay. So I should make it. So here is a statement about the dichotomy. It's again very busy transparency. You are not expected to understand every expression, but it just shows you that we have concrete, hands-on expressions which allow to make all judgments we need. In quite general setting. So let me see what they want to comment on this. So what the most important comment here, that for the space LL1, which corresponds to the high quality factor low loss modes, we have the following expression, and where CB is a function which defined like this. So as beta approaches infinity, CB approaches 0, and this quantity approaches infinity. So this is now a theorem, general theorem, that for the low loss modes, quality factor approaches infinity. And better than that, we have an estimate from below how it approaches infinity. Actually, almost linearly. If you consider this formula for large beta, it's almost linear. So now, some subtleties of overdamping phenomena. Introduction of gyroscopy make things more subtle in certain aspects, as expected. For example, as far as overdamping is concerned, and so we have here also an important technical achievement which we refer to the partial overdamping. There are theorems out there which say if you have loss matrix full rank, which means all degrees of freedom are susceptible to losses, then everything will be overdamped for fixed beta. So at some point, for finite beta, they become always all overdamped. But if the rank is not full rank, then it becomes much more subtle issue. And so we managed to handle it, and we call it partial overdamping. We can trace exactly which degrees, which modes, and how many of them will be overdamped, and how many will not be overdamped. And this issue is estimates, and this issue becomes more subtle for overdamping, but good news is that generically, the same effects occur for gyroscopic system, but there could be exceptions, and we have examples when this exception can occur. We don't have, full an algorithm which determine it simply, but we have example, and we have a statement about that generically that the analysis which we have holds for gyroscopic case. So here is the theorem of selective overdamping. Again, this is formally written mathematically, a statement, how many modes are overdamped and how they split in these classes, okay? So this is again a precise statement how overdamping occurs with all parameters well defined that first high loss modes are overdamped, then another threshold, beta 2, after we can observe all overdamped modes and say exactly where they are. Some of them, so they split into classes. High losses are always overdamped, and low losses class, this for we introduce LL with index L0, also overdamped. And in between, different things can happen. And here is also, we derive precise asymptotic formulas for all quantities of interest. Also very busy transparency, will take probably 15 minutes to explain every notation, but you can be assured that all these quantities can be explicitly traced to original matrices with pretty much explicit representation. So I have very little time. Now we take electric circuit example, revisit it, taking these general statements which we derived. We find all these quantities we used in general theory, their representation in this concrete example, also explicitly written asymptotic formulas. Let me see, I want you have very little time, so I just want to show you one transparency. So an interesting statement, how accurate is asymptotic formulas. So here on this transparency, these crosses correspond to asymptotic formula, whereas the rest is precise calculation, shown in a graph. You cannot distinguish this by naked eyes, they're so good. Okay, probably I should finish here. Thank you.